YouTube channel. So today we are going to finish up the part 3 of the Lewis structure and also valence shell electron pair repulsion. So the outline for this part 3 is after this part, okay, you will be able to predict the shape or geometry based on VSEPR. So here in this slide, okay, we have five basic molecular shapes. Okay, they are linear, trigonal planar, tetrahedral, okay, trigonal bipyramidal, and also octahedral. Okay, so all of these are 5 basic molecular shapes without any lone pair. Okay, so for the first one, let's go to the linear shape or linear geometry. Alright, so for this linear, the angle for this is actually 180 degree. Okay, the class is AB2, or you can write it down as AX2. Right, so how many atoms bonded to the central atom? We have 2 and with 0 lone pairs. Okay, so in order for you to draw this molecular geometry, so you need to have the central atom and also surrounding atoms with 180 degree. So here, this is one example of the linear geometry. Okay, so for example, let's say we have the beryllium difluoride or beryllium fluoride. So the beryllium will be the center atom because of the least electronegative, and then surrounded by the 2 fluorine atoms, okay, with the lone pair surrounding the fluorine. So here, okay, the angle between fluorine, beryllium and fluorine must be 180 degree. Okay, and then other than that, we go to the second one, the trigonal planar. Okay, so the class here is AB3, or sometimes you can write it down as AX3, and the atoms bonded to the central atom is 3, while we have 0 lone pairs, okay, on central atom. And okay, the angle between the surrounding atom, okay, this is the surrounding atom, okay, and the central atom here, for example, is the BAB, must equal to 120. Okay, so other than that, other than trigonal planar, if we have one lone pair, okay, one lone pair on the central atom with the 2 surrounding atom, okay, and we write it down as AB2E, E equals to lone pair, or you can write it down as AX2E. Okay, so this one will give you this kind of shape. Okay, one lone pair on the central atom and 2 surrounding atom, okay, 2 surrounding atoms, okay, 2 surrounding atoms, the B here, and the shape that we can have here, or the molecular geometry here, is bent. Okay, other than that, we can call it as V shape. Okay, V shape, because it show you the shape of V. Okay, right, so this is the 2 molecular shape, okay, that we have discussed, trigonal planar and also the B or V, trigonal planar and also the band or V shape. Okay, so here for the trigonal planar, we must have 120 degree, okay, and the class is AX3 or AB3. Okay, while for the band, okay, this one will become as AX2E or AB2E with the presence of 1 lone pair, okay, at the central on the central atom. Okay, and for example, for the trigonal planar, okay, Here we can have SO3, BF3 and so on, while for the example for the V shape, okay, and here is SO2, ozone and so on, okay. So this band, okay, shape is actually comes from the original shape of the trigonal planar. Okay, other than that, we go to the tetrahedral, or where we have the four surrounding atoms to the central, bonded to central atom with a 0 lone pair, okay, with the class of AB4, or you can write it down as AX4. Okay, so the angle for the tetrahedral here is 109.5, okay, alright, here, okay, with four surrounding atoms. And then if we have, okay, one lone pair, okay, on the central atom, and we write it down as AB3E, okay, because we have three surrounding atoms, okay, bonded to central atom. Okay, so it will give you one lone pair and three bonds here, and the shape here will be trigonal pyramidal. Okay, the trigonal pyramidal with one lone pair. Okay, and then if we have two lone pairs surrounding the, or two lone pairs on central atom, and two atoms bonded to central atom with AB2E2 or AX2E2, it will give us shape of band or molecular geometry of band. Okay, for example is the H2O, where we have two lone pairs and two surrounding atoms. Okay, and then these are the examples for these three molecular shapes actually come from tetrahedral, or it has a structure of tetrahedral. Okay, so first thing is we have tetrahedral, and then second one we have trigonal pyramidal with one lone pair, and then last but not least we have band or V shape with two lone pairs surrounding the central on the central atom. Okay, so these are all the examples of the three molecular shapes of the tetrahedral. And then other than that, okay, so here we have the relationship, or what we call the bonding pair and lone pair repulsion. Okay, so from this diagram, okay, from this diagram we have three conditions or three situations. First one, we don't have any lone pair, but we have the bonding pair. Okay, we only have bonds here. Okay, 4 bonds here. So the angle of the HC and also H here is 109.5. While for the second situation, where we have one lone pair, okay, on the central atom, which is nitrogen, with 3 bonds here, okay, the angle between the hydrogen, nitrogen and also hydrogen here is 107.3. And okay, so this is the first one, second and also third one. While for the third one here, we have 2 lone pairs on the central atom of oxygen, while for the bonding here, HOH is 104.5. Okay, why this happened? Okay, this is because, okay, because of the, if we have the lone pair and lone pair repulsion, they are they required, okay, much more energy and more repulsion between the electron pair, between the lone pair and also the bonding. So what happened here, they start to repel, okay, this angle. Okay, so because of we know that lone pair has greater energy. Okay, so what happened here, the angle here will become smaller. Okay, that's why lone pair versus lone pair repulsion is bigger compared to the lone pair versus bonding pair repulsion here. For example, for the second one, And then this one is much more bigger than the bonding pair versus bonding pair repulsion. Okay, so this is what happened here if you have the lone pair and also bonding pair. Okay. Okay, so this is 109.5, this is 107.3, and last but not least 104.5. Okay, and the fifth one, okay, with so this is the fourth one, okay, of the structure with no lone pair at all, okay, zero lone pair on central atom, and we have 5 bonded surrounding, okay, or what we call surrounding atoms to the central atom, 5, with the class of AB5 or AX5 here. So the shape or the molecular geometry that we have for this class is trigonal bipyramidal. Okay, so for the trigonal bipyramidal, here we have two angles. Okay, first one is we have 90 degree and the second one is 120 degree for this, okay, planarity here. Okay, then here if we have one lone pair, okay, with the 4 atoms, okay, bonded to central atom with the class of AB4E or AX4E. So other than trigonal bipyramidal, it will become distorted tetrahedron. Okay, distorted tetrahedron where it has one lone pair, okay, on the central atom and 4 bonding or 4 bonds, okay, surrounding the central atom. So this one will become distorted tetrahedron. Okay, then other than that, if we have 2 lone pairs on central atom and 3 atoms bonded to the central atom, okay, with the class of AB3E2, it will become T-shape. Okay, T-shape. So for example, here we have ClF3. This is the ClF3 with the T-shape. Why? Because the shape here is look like the T-shape, okay, with the 2 lone pair here at the central atom. Okay, other than that, if we have 3, okay, if we have 3 lone pairs, okay, on central atom and 2 atoms bonded to central atom with the class of AB2E3, this will become as a linear. Okay, for example, here we have I3 minus. Okay, right, so it should be I3 minus here. Okay, alright, and then here these are examples for the 4 molecular shapes of trigonal bipyramidal electron group arrangement. Okay, so the basic one here is the trigonal bipyramidal. Okay, this is the trigonal bipyramidal, and then we have the seesaw or distorted tetrahedron. And then we have the T-shape here. Okay, the T-shape with the 2 lone pair. And then we have linear. Okay, we have linear with the 3, right, lone pair at on the central atom. And the seesaw here, okay, this is the seesaw, should be like this with 1 lone pair here. Okay, and then and then last but not least, with the basic geometry, okay, we have octahedral AB6. Okay, the class here is AB6 or AX6. Okay, with the 6 surrounding atoms. Okay, and then the shape here is octahedral with 90 degree. Okay, and then other than that, if we have one lone pair with 5 surrounding atom, okay, with AX5E, right? So, or AB5E. So it will give us a square pyramidal geometry. Okay, a square pyramidal geometry. This is the shape of square pyramidal geometry. Okay, and then other than that, if we have 2 lone pairs and also 4 bonded atoms, okay, 4 atoms bonded to central atom, AB4E2, this will give us as a square planar. Okay, where we have a planar here with 2 lone pairs, okay, on the central atom. So these are the 3 molecular shapes, okay, of the octahedral electron geometry arrangement. So we have octahedral, okay, so these are the examples of the octahedral, AX6 or AB6. We have square pyramidal with 1 lone pair, okay, and then 5 bonded atoms, and also last but not least a square planar with 2 lone pairs on the central atom with 4 bonds here, okay. So based from the electron repulsion, okay, or what we call VSEPR, VSEPR, so we actually can predict the molecular geometry based on the electron repulsion. So how? Okay, first thing first, you need to draw the Lewis structure. Okay, so this is what I have explained to you in the part 2, where we have 5 steps, okay, in order to draw the Lewis structure for a molecule. So if you still remember, for the first part, for the first until to the last step, you need to be able to draw the Lewis structure for the molecule. And then other than that, after that, you need to count the number of lone pairs on the central atom, and you need to determine the number of atoms bonded to the central atom, or we call it as surrounding atoms, okay. And then last but not least, you need to use the VSEPR to predict the geometry of the molecule. So we have plenty shapes or geometry of the molecules here. So the question here, okay, what are the molecular geometries of the SO2 and also SF4? Okay, so the question here, what are the molecular geometries of the sulfur dioxide and also tetrafluorosulfide? So here we have the structure of the SO2 with Lewis structure, and then the shape here is a band, while for the tetrafluorosulfide here we have the shape of AB4E, or we call it as distorted tetrahedron, or other than that we call it as a seesaw. Okay, alright. So in order to get these two structure, you need to draw the Lewis structure, and second one, you need to determine the presence of the lone pairs, okay, or you need to count the number of lone pairs, and here we have 1 lone pair on the central atom, while here we have also 1 lone pair, okay, on the central atom, okay. But this one we have 2 bonding pair, we have 2 bonding, 2 bonds here, and then for this example we have 4 bonds, okay. Right, other than that, I have a problem here. Draw the molecular shape and predict the bond angles, okay. So for the first one is trifluorophosphide, and also second one is COCl2. Okay, so first thing first, as usual, you need to draw the Lewis structure. So this is the Lewis structure of PF3 with 1 lone pair on the central atom. Okay, it is actually based upon the tetrahedral arrangement, but with the 1 lone pair here. So what happened here, the final shape is trigonal pyramidal, because we have the lone pair versus bonding pair repulsion here. Okay, and the type of shape is AX3E. Okay, and then yes, this is for the A. Alright, and then guys, please do the B. Okay, we will discuss during our virtual class. Okay, and then another problem here, we need to determine the shape, okay, of each of the central atoms in acetone. Okay, so you need to draw the Lewis structure of the acetone. So, and second step, you need to determine which one is the central atoms. Okay, in this problem, we have more than one central atoms. Okay, so this central atom is this carbon, okay, second carbon and third carbon. Okay, right. So for this carbon 1 and also carbon 3, we have shape of tetrahedral or tetrahedral geometry. While for the, okay, why? Because we have the X4 with no lone pair. Okay, while for this carbon here, carbon 2 is the trigonal planar. Okay, why? Because we have 3 bonds, okay, surrounding the carbon. Okay, 4 bonds here, but this one is a double bond. Okay, double bond, we count it as 1. Okay, so here we have 3, so this is as AX3. Okay, with yeah, the angles of this one will be much more than 120, while this one less than 120. Why? Because we have 2 lone pairs here. Okay, where it actually repel, okay, the bond or the angle here. Okay, so last slide for this topic or part 2, the figure 10.11, okay, where both of these two have tetrahedral centers of ethane and also ethanol. Okay, so for this ethane, okay, alright, so this is the carbon 1, this is carbon 2, both are having the tetrahedral centers or tetrahedral geometry because they have no lone pair surrounding the carbon 1 and also carbon 2. While, okay, for the ethanol, both of carbon 1 and also carbon 2 also have the same tetrahedral geometry. Why? Okay, because there is no lone pair at all, okay, on the central of C1 and also C2. Okay, alright, but for this one, I will show you later, or I will explain to you later in next topic, which is hybridization. Okay, alright, so guys, that's all for today. I hope you guys enjoy my video. Alright, and then last but not least, please don't forget to like, comment, and also subscribe my subscribe to my YouTube channel. Thank you everyone. Bye.